This session is about coding theory, and let's welcome the first talk. The topic is on code and learning with errors over function fields by Maxi Bomba.
So thank you for the introduction. This is a joint work with Alain Couvreur and Thomas de Bries-Alazar. And yeah. So in this work, we focus on search decision reductions for structured variants of the decoding problem. More precisely, what we did is we adapted techniques from ring LWE and module LWE to the coding theoretic setting using function fields instead of number fields. This new framework that we call function field decoding problem enables us to give the first such decision reductions for the decoding problem of quasi-cyclic codes and proves pseudo-random assumptions made in multi-party computation. But in order to motivate this work, I will first begin to present the Electronic Cryptosystem, which dates back to 2003, and which is one of the two main paradigms to build encryption on codes and on the decoding problem, and for which such decision reductions are very important to assess the security. But the idea is that Alice chooses a code completely random, for which she knows a short code word in the dual, generated by SK. She publishes her random code C, and Bob, who wants to encrypt one bit, so he will first choose a code word in C. He will choose an error of very small Hamming weight, actually the same as SK here. And if he wants to encrypt 0, he will send C plus E, a noisy code word. And if he wants to encrypt 1, he will send a completely random vector of length n. For decryption, Alice will use the knowledge of her secret key, and she will take the inner product between the received word and her secret key. And because the secret key is in the dual, when Bob sent the encryption of 0, that is to say, when he sent a C plus E, this is nothing else than the inner product between the secret key and the error. And since both are vectors of very small Hamming weight, that is to say that there are lots of zeros, this inner product will be 0 with very high probability. On the other hand, if Bob encrypted 1, he sent a random vector so that this inner product will be a random bit, so it will be 0 with probability 1/2. In other words, the knowledge of the secret key enables Alice to distinguish between a noisy code word, C plus E, and a random vector of length n. This is precisely the hardness assumption to base the security of this Electronic Cryptosystem, and it can be thought as a code-based analog of the decisional Diffie-Hellman hypothesis. Well, let's formalize a little bit. For the decoding problem, there is the well-known computational decoding problem, where you are given a random code represented by its basis, like here as a generator matrix. And you are given also a noisy code word, Ng plus E, with some constraint on the error, and you want to recover the message, M. But we can also define a decisional version, where you are given a random code G and a vector B, which is either completely random or a noisy code word of the form Mg plus E. And the goal is to distinguish between these two cases. So the second problem might seem to be slightly easier than the first one. But in fact, there is like a result from Fisher and Stern in 1996 that proves that basically these two problems are equivalent. So what that means is that the Electronic Cryptosystem truly relies, its security truly relies on the hardness of the computational version of the decoding problem, which is a problem that is well understood and studied for now 60 years, more than 60. So, okay, so far so good. We have a cryptosystem which is basically secure, post-quantum, but it's not really efficient. Indeed, the public key is a random code, so it's represented by a random matrix. So it's very huge. It's quadratic in the length of the ciphertext, for instance. And also the encryption is pretty slow. So in order to cope with that, One idea is to add some structure and to restrict ourselves to random codes, but in a specific family of codes. For instance, we can take quasi-cyclic codes. That is to say that there are codes that have bases formed out of multiple circulant blocks like this. Okay. And so now, in order to publish this Electronic matrix, you can only publish its first row and can deduce everything by applying this quasi-cyclic shift. But quasi-cyclic codes have also another very interesting property. They come with efficient encoding by the so-called polynomial representation. The idea is you can represent a vector of length n as a polynomial of degree at most n-1, and you can also represent a circulant matrix like that by the polynomial that represents its first row. And using this formalism, now the matrix vector product is nothing else than the product of polynomials in the quotient ring fq of x quotiented by x to the n-1. So using this formalism, if I give you a general matrix formed by multiple circulant blocks like this, for instance, with 2 blocks, and a vector a message m, and now a noisy code word of this form will be represented by a bunch of noisy product of polynomials in this quotient ring. So we can translate the decoding problems and we can restrict them to quasi-cyclic codes and translate it using this polynomial formalism. So now in the search version, you are given a bunch of samples A/B, where the collection of the A represents the random generator matrix, and the collection of the B are all of the form MA plus E and represent the noisy code word. And the goal is, as usual, you want to recover the message. You can also define a decisional version, which is a retranslation of the previous one. We want to distinguish between 2 situations. However, when you restrict yourselves to such structured codes, there is no reductions between the decisional version and the search version. And however, these problems, these structured variants, are at the core of the security of NIST submissions, such as the BIKE or HQC. And this lack of reduction was already pointed out by NIST in the report for the second round. So, and this is the starting point of this work, basically. So we can wonder, well, okay, how can we prove such a reduction? The idea that we had is, okay, so for codes and structured codes, we don't have such reduction. However, in the case of lattices, and especially for ring LWE, for instance, there exists such decision reductions that use tools from algebraic number theory, such as ideals in number fields and embeddings and so on. So we wanted to do something quite analog, and because we're using codes, which are like vector spaces in some positive characteristic, and we wanted to use instead function fields. And in fact, what we can say is that this ring, where we can do all the computations, this polynomial ring, can be actually seen as the quotient of a ring of integers in some function field, and I will explain everything later on. But the idea is, okay, so this is very small. It doesn't have many ideals, but okay, it has a rich arithmetic structure. And to pass from one representation to the other is just to add a new variable t and to cancel it by quotient t. So we can really see this quotient as a quotient of a ring of integers in the function field. And using a deep analogy between number fields and function fields, we can do well. We can build a reduction. This is the point of the talk. But first, before presenting our framework, I will recall quickly what's happening for lattices and ring LWE. In ring LWE, which is a framework introduced by Lubashevsky, Paikert, and Regev in 2010, you take a number field K, which is a finite extension of Q. This number field has a ring of integers, which is an extension of the usual integer set. And you also take a prime element that we call the prime modulus Q, which lives in the actual integers here. So in the search version, you are given a bunch of samples of this form, A and B, where B is A times S plus E, where S is a common secret that lives somewhere, and E are all sampled from a Gaussian distribution. And A is taken uniformly at random in this quotient OK mod Q. And the goal is to recover the secret. And as usual, we can define the decisional version similarly as before. But in this context, and in this paper by Mp68 and Regev, they introduced a search decision reduction. They proved that with some hypothesis on the number field they used and some hypothesis on the prime, you can prove that the decisional version is actually equivalent to the search version. And later on, in the years that followed, this hypothesis has been removed. Okay, so we have this framework for number fields. What about function fields? The idea is, as I mentioned earlier, there is a very old analogy between number fields, which are finite extension of Q, and function fields, which have so finite separable extension of the field of rational functions with coefficient in FQ. And by analogy, I mean that basically many properties, and most of the properties that you can think about for number fields in characteristic 0, you can find the same properties in positive characteristic using function field and the subject. Very naturally, now that we have this analogy, we can define our framework that we call the function field decoding problem, or FFDP, where now you pick a function field K, just this form. You have this ring of integers, which is an extension of the ring of polynomials. You take a prime modulus, which is an irreducible polynomial in this ground ring. And to be the most general possible, we also define some probability distribution on the quotient OK mod Q, which will be the distribution of the errors. So now on the search version, you are given a bunch of samples of this form, and you want to recover the message, and the decisional version is defined as usual. Okay, so now we have a very abstract problem. What about this? Before to be interested in the decisional version, we can wonder if the search version is actually hard. And what I can say is that here this problem is parameterized by the choice of the function field you use, the choice of the prime modulus, and the choice of the error distribution. And I mean, that's okay if you choose them carefully. So what matters is instantiation. If you choose them very carefully, for instance, if you take this function field here and the prime modulus to be here T, which is irreducible, obviously, you actually recover the decoding problem of quasi-cyclic codes. Exactly. So with this instantiation, the search version of the function field decoding problem is hard because this quasi-cyclic decoding problem is hard, and they are both exactly the same problems. Okay, so now we can basically we are ready to state the main theorem of the paper. If there is an algebraic hypothesis on the function field, namely we want it to be Galois, and we want its field of constant to be not too large, so we won't go into detail also. If the prime modulus decomposes nicely into this ring of integers, and maybe one of the most important if the error distribution is invariant in the direction of the Galois group, namely to say like if some element X is distributed with respect to psi, I want, and I take any automorphism in the Galois group, I want sigma of X to be distributed with respect to psi also. Then we can prove that both decisional and surge version are equivalent. And actually, those three hypotheses are basically the same as what happened for ring LWE in this first paper. And the proof follows. We need to make some translation somewhere, but basically the proof follows this paper. Okay, so as I said, what matters is instantiation. So we have a very generic framework, a very abstract theorem. What about instantiations? So we need a Galois function field. We need to understand how prime elements decomposes into this. And we want to be able to define a probability distribution that is invariant in the direction of the Galois group. So for ring LWE, it was proposed initially to use cyclotomic number fields for many reasons. Okay, why don't we do that for function fields also? And yeah, there are many ways to define analog of cyclotomic fields in the situation of function fields. And there are many basic bad ways. And here I will present the one way that gives the best analogy between with cyclotomic number fields. And the idea to understand the construction is to look at what happened when we build cyclotomic number fields. Cyclotomic number fields are built by adding the roots of unity to Q. And in a very pedantic way, you can say that actually the roots of unity are the torsion element of some Z module structure on the algebraic closure of Q. Well, we can do the same by keeping in mind that Z is the analog of the polynomials. We can do the same and consider a new FQ of Z module structure on the algebraic closure of T, and we can add the torsion element to this field. Okay, to define this action, I will associate to any polynomial in T a new polynomial bivariate in X now. Recursive, and the definition is recursive. So the bracket of 1 will be just the polynomial X. The bracket of T will be defined as X to the Q plus T times X. And I propagate everything by FQ linearity, and I want the bracket of a product to be the composition of the brackets here. So I give here two examples, and to prove that we can basically compute such Kalitz's polynomial. And now the new structure we can add is the following. I can so a polynomial M will act on this algebraic closure by just the composition, well, the evaluation of the bracket of M on this element. And this has a name. It's called the Kalitz's module because it was discovered by Kalitz and his student Ace in the 1970s. And so now the M torsion elements, so I fix an polynomial M. The M torsion elements are nothing else than the roots of the bracket. And adding this M torsion element will give what I will call now the cyclotomic function fields. And they have many like properties, but the most important one is the following. It's the Galois extension, and the Galois group is easily computed to be the invertible modulo M. And why do I say that they are very like similar to cyclotomic number fields? It's because basically all the properties that you can think of in the cyclotomic number fields, you can have the same by replacing groups and subgroups by modules and submodules. And for instance, here, the Galois group of a cyclotomic number field was the invertible modulo N, and now the Galois group of the Kalitz's extension or cyclotomic function field is the invertible modulo M, where M is the defining polynomial of the torsion. Okay, let's do a quick, simple computation to understand what's happening. I recall that the bracket of t was x to the q plus t times x. What about the t torsion? The t torsion is just the roots of this polynomial, so it's 0 plus all the q minus 1 roots of minus t. In the algebraic closure, it makes sense. So when I add this torsion element to fq of t, I have this function field, which is generated by this polynomial. I can compute the ring of integers, which has this very nice shape. And I recall that the Galois group was the invertible modulo the defining polynomial of the torsion. So here it's just t. And the invertible modulo t are just the non-zero constants. And now I can also look at this ring of integers and quotient it out by some irreducible modulus. T plus 1 is obviously reducible because it's of degree 1. And this quotient is exactly fq of x, quotient out by x to the q minus 1 minus 1. Right? What do I miss here? The only thing that is left now is to understand the action of the Galois group on this quotient. And so, as I said, the Galois group is the non-zero constant, and actually you can compute this action on this ring by the following: a polynomial in this. Well, okay, so a non-zero constant will act on the polynomial in the quotient by just the multiplication by zeta here. So because zeta is non-zero, it means that the action of a non-zero element, so an action of the Galois group here, will leave invariant the Hamming support of the polynomial p, which means that any error distribution that depends only on the Hamming support will be invariant under the action of the Galois group. So, for instance, the Bernoulli distribution will be invariant under the action of the Galois group, or the uniform distribution on all words of specific weight will be also invariant under the action of the Galois group. So all in all, if we plug everything together, what do we have is that actually the decision version of the decoding problem for codes based on this ring is equivalent to the actual computational version of the decoding problem. And actually, this precise assumption has already been used to design pseudo-random correlation in secure multi-party computation. So they used the hardness of this decisional version to build their scheme. And now with this work, we can prove that, well, if you have confidence in the decoding problem of quasi-cyclic codes, then, well, the decision version is hard. Okay, it can also generalize to other like group codes. I won't go into detail, and can also apply to several variants of ring LPN. And there is also a module version, which is, well, basically just a very natural generalization when we have everything here. Okay, so just to conclude, so on the left of this table, I put some very interesting and important milestone in the ring LWE history. The first one, 2010, is the first paper by Lobachevsky, Paikat, and Regev that introduced this problem, and the first such decision reduction that used cyclotomic number fields and special arithmetic hypothesis on the modulus. In this work, we give an analog when we take a function field to be Galois, and we take also the same specific arithmetic hypothesis. But since 2010, there has been improvements. And for instance, there is a paper by Langlois and Stille when they removed this modulus hypothesis here. And more recently, and this is maybe the most important work here, there is a paper by Paikat, Regev, and Stefan Davidovits here in 2017, and by Stille, Vallet, and Roska in 2018, where they give a completely different framework called Oracle with Hidden Center problem, to prove a search to decision reduction for any number field. Okay, and actually, if we could extend this result to any function field, it would apply to codes that are used in the NIST submissions, such as bike and HQC, because we could actually use the function field that I introduced in the beginning of this talk, and we could have this search to decision reduction for those codes. But unfortunately, now is it doesn't. Well, it's already useful, but there is still work to do. Thank you.
While the next speaker prepares for the talk. Oh, okay. Yeah, good. Yeah, go ahead.
Just a quick one. Thanks for the nice talk. Can you say something about the sample complexity of your reduction?
Okay. So we can well in the paper we give explicit formulas about like the time complexity here. Well, the thing is that the number of samples in our FFDP problem is related to the rate of the code that is underlying, because well, the rate of the code is basically the inverse of the number of samples, right? Okay. I'm not sure it answers your question. Well, okay, we can talk about it later. Sorry.
Okay. Since we are running a little bit late, let's thank the speaker again. The next talk is syndrome decoding in the head, short signatures from zero knowledge proofs, by Thibault Fanel. Hope my pronunciation is
Thank you for the introduction. So I'm Thibault Feneuil, and today I'm going to present you this joint work in which we propose a new code-based signature built from a zero-knowledge proof. Thank you. So to design our signature, we chose to focus on the syndrome decoding problem for random linear code. This problem consists, given a matrix H and a vector Y, to find a X such that we have the linear relation Y equal to X H, HX, and such that the Hamming weight of X is less than some bound W. This problem is known to be NP hard, and its cryptanalysis is stable for many years, especially for the binary field. Our goal is to build a zero-knowledge proof of knowledge for this problem. More precisely, we want to design a protocol where a prover wants to convince a verifier that she knows the solution of a syndrome decoding instance without leaving any information about the secret itself. To build this zero-knowledge proof, we will rely on the Mp68 paradigm introduced in 2007 by this famous article of Stock. This paradigm provides a generic method to build a zero-knowledge proof using techniques from secure multiparty computation. This paradigm works as follows. We have our secret which satisfies those both relations. We will first share our secret in n parts, n shares, x1, xn, so that the sum of the shares are equal to x. Then let us assume that we have an Npc protocol which takes as input the shares of the sharing of x, and he will check that the shared vector is a solution of a syndrome decoding instance. We will use this Npc protocol in a black box manner to build our zero knowledge protocol. The prover, the honest prover who knows the secret, will run this Npc protocol in her head, meaning that it will run the computation of all the parties involved in the Npc protocols. Then it will commit the computation, the view of each party independently. Then the verifier will ask to reveal the view of all the parties except one. And then it will check that the revealed views are consistent between them. A malicious prover doesn't know an input sharing so that the Npc protocol output accept. Output accept. So he will need to cheat on the computation of at least one party. But it means that the cheating will be revealed, exposed, as soon as the verifier will ask to reveal the view of the cheating party. Here, I assume that we had an Npc protocol that check if a vector is a syndrome decoding solution. But in practice, we need to design to choose this Npc protocol. And the performances of the zero knowledge proof will highly depend on this protocol. From this slide, all the red values are values which contain information about the secret X, so which must never be revealed. We want to design an Npc protocol which checks those both relations. The linear relation is easy to check in MPC, but it's much harder for the constraint about the Hamming weight. For this reason, we will replace the second constraint by an equivalent one involving polynomials. This new constraint consists to prove the existence of two polynomials, such that we have the following relation SQ equal to PF, where S is defined such that the evaluation of some public point correspond to the coordinate of the tested vector. And the polynomial F is the smallest polynomial which has for roots all those evaluation points. We add the constraint also that the degree of the polynomial Q is W. Let's assume that we have this relation on polynomials is satisfied. We can deduce the following statement. When we evaluate the product QS by the public point gamma I, we will get 0 because it's gamma I is a root of F. So either the evaluation of Q is 0 or the evaluation of S, meaning the coordinates of X, is 0. But since the degree of Q is W, the first case can occur at most W times, implying that the rest of the time is the second case which occurs. And so we get directly that the Hamming weight of X is less than W. In practice, such polynomial Q can be easily built from the secret vector. We just need to take a monic polynomial of degree W so that the non-zero position of X are encoding as roots. Then we can deduce the polynomial F using the previous formula since the F divides the product SQ. Now that we have the exact statement we want to prove in the Npc protocol, we will describe the protocol we proposed in our work. We assume that our matrix H is in the standard form, meaning that the right part of the matrix is the identity matrix. Then, if we write the secret X as XA, XB, we get directly this linear relation between XB and XA. The input of our Npc protocol will be XA and the polynomial Q and P. And the aim of the protocol will be to check if XA corresponds to the syndrome decoding solution. The first step of the Npc protocol is to recompose the secret X using XA using the previous linear relation. Then we can build the polynomial S by interpolation, so that the evaluation of the polynomial are the coordinate of the tested vector. In practice, we can easily do that in Npc, since the interpolation formula is linear into the secret value. Finally, we need to check the wanted relation on the polynomial. However, checking directly this relation in Npc cannot be easily done efficiently. So we will proceed as follows. The parties involved in the Npc in the multi-party computation will get a random point R, a common random point R, sampled from a field extension of the field where live the polynomials. Then we will compute the evaluation of S, Q, and P in this point R. Finally, we will use the sacrificing techniques from the BN20 protocols to check the wanted relation evaluated to the point R. That is the protocol we use in our work. Let's remark that we don't prove the constraint on the degree of Q because it's explicitly already done. In practice, Q is a monic polynomial, meaning that the leading coefficient of Q will be 1. And so we don't need to share. It's not a secret, so it will be revealed. And so we directly get that the degree of Q is W. Even if XA doesn't describe a syndrome decoding solution, sometimes the Npc protocol will output accept in two cases. Even if we don't have the wanted relation, we can have the equality for a given point. But this case will occur with only small probability, and this probability is given by the Schwarzschild lemma. The second case is then the BN20 protocol fails to check the relation. And this case occurs only with small probability, which is 1 over the size of the field where is sampled the point R. To summary about the Npc protocol, we have a protocol that checks if the input is a syndrome decoding instance. If it's the case, it will always output accept. And if it's not, it will reject with high probability, and it will accept with small probability, and this probability can be deduced from the last two cases of the previous slides. Now that we have the Npc protocol we will use in our work, we can directly apply the Mp68 paradigm to get a zero knowledge proof of knowledge for the syndrome decoding problem. The first step of the prover will be to build the polynomials Q and P. Then it will commit the inputs of each party independently. Then the verifier will choose the evaluation point R, and will send the evaluation point R to the prover. And now the prover can run the computation, described as follows. It will run the computation for all the parties. It will send back to the verifier all the communication broadcast by the parties in the subroutine BN20. And finally, the verifier will ask to reveal all the views except one, and will check if those views are consistent. The soundness error of this protocol, meaning the cheating probability of the prover, is given by this formula, where P is the small probability we saw in the previous slide, and N is the number of parties involved in the secure multi-party computation. When relieving the view of all the parties except one, the prover will need to send the inputs of n-1 parties. In practice, the input share are built as follows. For all the parties except the last one, a share will be generated from a seed using a pseudo-random generator. For the last party, the share will be computed such that we have the wanted equality. It means that for all the parties except the last one, the prover just needs to send a seed of lambda bits, where lambda is the security level of our scheme. And for the last party, the prover needs to send the uncompressed shares. Then in the proof, we need to add some additional element due to the BN20 subroutine as a communication broadcast by the parties. And finally, we can apply several optimization to decrease the security, the proof size, like seed tree. Now we have our zero knowledge proof of knowledge. We can apply the Fiat-Shamir transform to get our signature scheme. The idea is simply to replace the verifier challenge by the output of a hash function, which take as input the message we want to sign, and the data previously sent by the prover. Since we transform a 5-round zero-knowledge protocol into a signature scheme, we need to take into account the attack of Kales and Zaverusha. We need to take into account this attack. In practice, we will use this attack, this formula, to select our parameter sets for our signature scheme. In our work, we propose 3 parameter sets for a security of 128 bits. The first one relies on the binary field. Then the field in which the polynomial lives must be a field extension of this field, and must have enough point to interpolate the polynomial S. So in this case, the field must have at least 2 to 11 elements. To add more flexibility and to decrease this the size of this field, we proposed another variant. It corresponds to a syndrome decoding still on the binary field, but instead of proving a Hamming weight for all the secret X, we will split our secret into 6 chunks, and we will prove a local Hamming weight. These local checkings will decrease the security of the syndrome decoding instance. And we can take bigger instances for the syndrome decoding to mitigate this security loss. With this variant, the size of the field is now 2 to 8 elements. Finally, we can directly take a variant defined on the syndrome decoding instance over a larger field, so that we have directly that the field for the polynomial is the same as the field for the syndrome decoding instance. Here are the performances of our scheme. We propose, for each variant, we propose two trade-offs. The first one will lower the communication cost, when the second one will lower the computational cost, meaning the running time of the proof, the signer and the verifier. Let us compare our scheme with all the former signature scheme built from zero-knowledge proofs. We can observe that our scheme is outperform all the previous one regarding the size of the signature. We are the first scheme which we can produce signature using the last variant, signature size below the symbolic cap of 10 kilobytes. Now, let us compare our scheme with all the other code-based signature. We are far to have the smallest signature size. However, in some use case, we need to take into account the size of the public key. And if we compare all those schemes regarding the sum of the size of the public key and the signature, we outperform all those schemes. We can produce a signature for which the sum is below than 10 kilobytes. We can add that all the scheme, most of the scheme use a less conservative assumption, or less like a structure problem. To conclude, in this work, we proposed a new code-based signature built from zero-knowledge proof. This signature is a conservative scheme since it relies on the security of the syndrome decoding problem without structure. And it remains competitive regarding the sum of the size of the signature and the public key. As future work, we plan to optimize the implementation, and we search parameter sets which would provide better performances. Thank you for your attention.
Any question?
Yeah. So I wonder if this benefits at all from preprocessing or like not at all.
Oh, can you repeat, please?
Yeah, so there are like these zero-knowledge techniques based on MPC in the head that if you have certain computation that you can push to a preprocessing phase that is independent of the inputs, then you can get benefits. I wonder if you could look at that.
So you ask to compare with work with preprocessing phase?
No, if you can optimize your protocol so that there is a load that goes to the pre-processing phase, and that way you can get benefits.
In fact, this work, we succeed to have a small signature size using this by rephrasing the statement we want to prove. And so we cannot apply this technique with all the problem we want. We need to see if the statement we want to check is compatible with this technique. But it's not a generic technique.
All right, thank you.
Yep, please go ahead.
Hi, thanks for your talk. So just to have a quick question about your concrete instantiation. So do you pick the gamma i's arbitrary or is there any like strategy?
So you ask if the gamma I, the evaluation point can be arbitrary. Yes, it's any field element. It just be distinct. It's the only constraint.
Okay, thanks.
I also have a question. So I saw in the on your previous slides, there are some kind of variations on the public key and the signatures, and you are mostly optimizing on the signature size. Would it be feasible to actually shift most of the size to the public key and make the signature very, very, very small, look like a rainbow stuff where public key, it's all like a wavelet, that kind of stuff. Is that feasible?
In fact, when we work on we transform a zero knowledge proof into a signature, all the scheme get a very short public key because it's just a seed. Since the problem is unstructured, we can just take a seed, and so we cannot transfer the size into the public key. It's due to the technique of Fiat-Shamir, of transforming the zero knowledge proof into a signature scheme. So no, we cannot transfer the size into the public key size.
I see. Okay, thanks. If we don't have any more questions, let's thank the speaker again. The next talk is Beyond the Seas Corner Bound, Best Possible Wiretap Coding by Obfuscation. And the speaker is Alexis Korb.
Hello, my name is Alexis Korb, and I will be presenting our
one
work on
one
Beyond the
moment,
Corner
please.
Bound,
My
Best
apologies.
Possible Wiretap Coding via Obfuscation. This is joint work of Yuval Shai, Paul Loon, and Mitsahai. So we begin by defining the wiretap channel, which was first introduced by Weiner in 1975. So in this model, Alice wishes to send a message M to Bob by sending an encoding of M across Bob's channel, channel B. However, there exists an eavesdropper, Eve, who also receives the encoding across her eavesdropping channel, channel E. So Alice's goal is to send the message M to Bob without Eve also learning it. So in this model, we consider the case where Bob's channels and Eve's channels are both discrete memory list channels. So by this, we mean that we can define a channel as a function which maps every input symbol to each output symbol with some fixed probability P, which is dependent on the channel. So individual inputs are mapped independently to outputs based on these probabilities. And furthermore, we consider the case where the input and output alphabets are fixed constant size. Okay, so so in this model, we also consider the non-interactive setting, which means that Bob cannot send messages back to Alice. And we also assume that Alice and Bob have no shared secrets ahead of time. Okay. So more formally, we can define an encoding and decoding scheme to be a secure wiretap coding scheme for a wiretap channel defined by Bob's channel and Eve's channel if it satisfies two properties. So our correctness says that if you have a single bit message and you encode it and then send it across Bob's channel, then the decoding algorithm should output the message with high probability. And security says that Eve cannot guess the message. So if you have a random single bit message, you encode it and you send it across Eve's channel, then the probability that the adversary guesses the message should be no better than 1/2 plus negligible. So we can also define this in the computational setting. So here we require that Alice, Bob, and Eve are all computationally efficient. So security is only against efficient adversaries, and we require that the encoding and decoding schemes are also efficient. Furthermore, results do generalize to the larger message spaces. So the message doesn't have to be a single bit. And let's talk about rate. So to sort of characterize this, we'll just begin with a simple impossibility. So we note that if Eve can perfectly simulate Bob's channel, then there's no hope of having a secure wiretap coding scheme. And this is because Eve can essentially learn everything that Bob can learn. So we can say if channel B, if Bob's channel is a degradation of Eve's channel, if Bob's channel can be written as the concatenation of Eve's channel with some other channel, channel S. And so in this case, Bob has no advantage over Eve, so we cannot securely send a message to Bob without Eve learning it. So just as an example of this, suppose that Bob's channel is a binary symmetric channel, which flips each bit with probability P, and Eve's channel is a binary erasure channel, which erases each bit with some probability 2P, so twice Bob's flip probability. In this case, Eve can simulate Bob's channel because with roughly 2P erasures, she can just assign each erasure to a random bit. Roughly half of those will be correct, so she'll end up with a string with about P bit flips. And that's exactly what Bob's channel does. So this is just a simple example where Bob's channel is a degradation of Eve's channel. And in this case, wiretap coding schemes are impossible. Okay, so in light of this result, we can ask whether it's possible to create a secure wiretap coding scheme whenever this is not the case. So can we create a wiretap coding scheme whenever channel B is not a degradation of channel E? So unfortunately, in the information theoretic setting, the answer is no. So Cesar and Corner in 1978, and these are the Cesar and Corner of our title. They show that wiretap coding schemes are possible if and only if channel E is not less noisy than channel B. Okay, so there's a little bit of double negative here. We say not less noisy instead of noisier. And the reason is this is not really a linear relationship. And in fact, two channels can both be not less noisy than each other. And I'll explain this more on the next slide. Okay, so what is not less noisy? And recall, this is the case when wiretap coding is possible. So this kind of looks like our diagram from before. So we have that channel E is not less noisy than channel B if there's some message distribution and some single symbol encoding of the message distribution such that Bob has an advantage over Eve in learning the message M. And here by advantage, we mean that the conditional entropy of the message given Bob's output Y is less than the conditional entropy of the message given Eve's output Z. So in this case, again, the encoding is only a single symbol as opposed to a large string, and we're defining this advantage in conditional entropy. So one thing to note is that this is a bit different from channel capacity. So channel capacity says you take the best input distribution for Bob and the best input distribution for Eve, and you compare the respective rates of information that can be sent across both. In this one, we're saying you take a common shared distribution X, and you see if you can create one that favors Bob's channel over Eve's channel. And in general, this is probably not rate efficient for either channel. And in fact, there are some input distributions that favor Bob's channel, or maybe there's other ones that favor Eve's channel. So it can be the case that they're both not less noisy than each other. So yeah, so all we're asking is there's some message scheme, some encoding scheme that favors Bob's channel over Eve. And in fact, Eve can have higher channel capacity than Bob and still have this be the case. Okay, so just to characterize this a little bit more, the less noisy condition is stronger than degraded, which means that if Bob's channel is a degradation of Eve's channel, then Eve's channel is less noisy than Bob's channel, and therefore we have an information theoretic impossibility. And also on the graph on the right, if we consider where Bob's channel is this BSC with flip probability P, and Eve's channel is a binary erasure channel with erasure probability epsilon, then this entire blue section there is the area where it's impossible in the information theoretic setting. And remember, if the erasure probability is twice the flip probability, then we have degradation, which is sort of the x-axis and below on that graph. So as a very specific example, if Bob's channel has a 10% flip probability and Eve's channel has a 30% erasure probability, we have this information theoretic possibility, but we do not have degradation because the erasure probability is more than twice Bob's flip probability. Okay. So seeing as this has been very well characterized in the information theoretic setting, we can ask whether we can do better computationally. So historically in crypto, we've gotten a lot better results in the computational setting compared to the information theoretic setting. For example, secure encryption, secure MPC, and many, many other cases. And surprisingly, even though this was introduced by Winer in 1975, which was more than 40 years ago, to our knowledge, it's only really been studied in the information theoretic setting in terms of feasibility. So what we do in this paper is we solve this 40-year-old open problem and ask, can we expand the feasibility region of these channels in the computational setting? So that is the focus of our paper. So in light of that, we'll return back to our original question, but this time in the computational setting. So we ask, can we create a secure wiretap coding scheme whenever channel B is not a degradation of channel E? And recall that our simple impossibility, where Eve can simulate Bob's channel, also holds in the computational setting. So in our work, we show that yes, assuming a form of evasive function obfuscation, then wiretap coding schemes are possible if and only if Bob's channel is not a degradation of Eve's channel. So in fact, this is the best possible region we could hope for in the computational setting. And this greatly expands the region from the information theoretic setting. And there's one note, actually, the only computational assumptions we need are for this function obfuscation here. And in fact, you can view our scheme. Sorry. You can view our scheme in the ideal obfuscation model, in which case our scheme is unconditionally secure against unbounded adversaries who are only allowed polynomially many queries. So really our computational results are only required for this obfuscation. So let's just go into what sort of obfuscation we need. So we can define a statistically evasive circuit, sorry, which is in general a circuit that almost always outputs 0, and for which it's hard to find an input on which it outputs 1. So more formally, if we have a collection of circuits D, and we have an auxiliary input generator box, then if you take a random circuit from that distribution of circuits, and you allow an adversary to have oracle access to that circuit with polynomially many queries, along with the auxiliary input, then the adversary should not be able to find an input on which the circuit outputs 1. And these are for unbounded adversaries. So in our setting, our class of circuits will be generalized fuzzy point functions for some random center R. And by this, we mean you pick a random center R, and then the function will output 1 if its input is close to that center, and otherwise it will output 0. And our auxiliary input will be Eve's channel on the center R. So in order for this to satisfy this definition, we require that even given this leakage on the center, you still can't find something that is close to the center for some notion of close. Then for our obfuscation, we require that our obfuscation satisfies 2 properties. So correctness says that the obfuscation of the circuit should have the same input-output behavior as the original circuit, except with negligible probability. And virtual black box security says that a simulator should be able to simulate the obfuscation given only oracle access to the circuit. So more formally, a simulator who's given polynomially many queries to the circuit, along with auxiliary input, should be able to produce an obfuscation that fools a distinguisher. And in our case, because our circuits are statistically evasive, then actually giving the oracle access to the simulator does not help very much. So yeah, so what is known about these circuits? There are no known impossibility results known because these are statistically evasive circuits, although there are some impossibility results for computational circuits. We can also conjecture that IO achieves this because IO is the best possible obfuscator, which means if there exists any scheme which achieves this, then IO also does so. And finally, there is a candidate construction in a weak multilinear map model that we don't know any tags for. So assuming this form of obfuscation, then we have the best possible encoding schemes in the computational setting. Okay, so how do we construct this? Let us return to the example we had before, which was this little point in the blue section. So recall, this is Bob's channel is a BSC with flip probability 10%. Eve's channel is a binary ratio channel with a ratio probability 30%. And here, Bob's channel is not a degradation of Eve's channel. So our simple impossibility does not hold. But Eve's channel is less noisy than Bob's channel, so it's information theoretically impossible to construct such an encoding. Okay, so just to characterize these channels, suppose you send a random message R across both channels. Then Bob should get something with 10% bit flips, and Eve should get something with about 30% erasures. And one thing to note is that because we don't have degradation, it's difficult for Eve to try to emulate Bob's output. So more specifically, if we asked Eve to try to create something with 10% bit flips, then Eve can't do so, because Eve's best strategy is just to assign each erasure a random bit, which gets about 15% bit flips. And therefore, she can't emulate this 10% bit flips. And so actually, even though Eve has higher channel capacity than Bob in this case, and she would know more about R with mutual information, she still gets a different type of information. And she can't emulate this type of information that Bob receives. So this is the key insight that we're going to utilize here. Okay, so in light of this is our scheme. Recall that Alice wishes to send a message M to Bob. So first, Alice will choose a uniform random string R and send it across both channels. And then next, Alice will construct an obfuscation of this function. And we can consider her as sending this to both Alice or Bob and Eve in the clear, but really she can use a encoding scheme for Bob's channel and send it across Bob's channel, and we don't require security. Yeah, so for this function is going to have R and M hard-coded into it, and it will output the message if its input has about 10% bit flips relative to R. Okay, so why do we have correctness? We have correctness because Bob can simply put his input into this obfuscation, and because it has about 10% bit flips, the function should output M, and therefore Bob learns M. And then security follows by our earlier argument. So as we said, Eve can't create inputs for which she has about 10% bit flips relative to R, even given her leakage RE. And therefore, we can argue that this function is statistically evasive. And therefore, our obfuscation will hide the value of M because we can replace this with a simulator. So Eve learns nothing about M. And in fact, more generally, this can work for any pair of BSC, BEC channels in the less noisy case. So this entire blue area we had before is now actually possible in the computational world, assuming this obfuscation. Okay, but again, this is just two channels, BSCs and BECs. What can we do just more generally? Okay, so more generally, recall that we wanted to create a scheme whenever we didn't have the degradation condition. So what does it mean when we don't have degradation? It means that no matter what channel S that Eve concatenates to her own channel, she can't emulate Bob's channel, which more specifically means that there's some input symbol X star and some input symbol Y or output symbol Y star, such that the crossover probability between X star to Y star is different when you go through channel B than if you go through channel E and then channel S. So this is what we'll utilize. Okay, so our scheme is fairly similar as before. Alice wants to send a message M to Bob. So first she picks a random message R and sends it across both channels. Then she'll create an obfuscation of the following function. So the function again has R and M hard coded into it. And it will check if every crossover probability is what would be expected if you had sent the input across, if you had sent R across channel B to get the input. So we'll check all the X's and R's and see how many of those became Y's in R prime and see, okay, is this ratio what I would expect if R prime was generated by sending R across channel B? So it's checking whether R prime, its input is sort of a typical value in terms of these input output ratios from sending R across channel B. Okay, so in this case, we get correctness again because Bob simply puts his input RB into this obfuscated function, and it should pass these checks with good probability, and therefore he gets M. And then what about security? So recall that if we said that if Eve cannot generate inputs to this function that cause it to output M or not bot, then we can sort of replace it with a simulator and hide the value of M. So really what we want to do is say that even given RE, her leakage, Eve still cannot generate any inputs that cause this function to output anything but bot. So that's what we're going to look at. And we first consider a restricted setting, where the only way Eve can generate these values is by running her input RE through a discrete memoryless channel, channel S. So suppose it's the case, Eve generates these R primes for whatever channel S's she likes, and then she tries to input them into the function and cause something to output M. So in this specific scenario, we can argue security. And why is that? Well, because channel B is not a degradation of channel E, then there should be some X star Y star with a different crossover probability between R and R prime than what you would expect if you sent it through channel B. And therefore, if you input R prime to this equation, when it checks for X star and Y star, it should notice that the crossover probability was different. And therefore, the check will fail and it'll output bot. And as we said earlier, if you can't create anything that doesn't output bot, then the obfuscation will hide the value of M because you can replace this function with a simulated one. Okay, but of course, Eve doesn't have to do that. Eve can choose any strategy she wants. In fact, this strategy can look at all the bits of RE at once and try to generate something. So how do we argue security in this case? Well, what we'll do is we show that, in fact, using this arbitrary strategy is no better really than if Eve had used a discrete memoryless channel, channel S. So more specifically, for any channel or any strategy G, then there's some discrete memoryless channel and some polynomial such that E's probability of producing an input that causes the function to output M is no more than polynomial times her strategy if you use channel S plus some negligible value. So in particular, if her probability winning in channel S was negligible, then E's probability winning with G is also negligible. And we show this via hybrid argument, but for the sake of time, I won't be able to go into that, but you can see our paper for details. Okay, so in conclusion, we show that assuming this form of function obfuscation, then wiretap coding schemes are possible if and only if Bob's channel is not a degradation of Eve's channel. So this means that this entire blue region of less noisy that was impossible in the information theoretic setting is now possible in the computation setting, and we have completely characterized the region. And one nice thing is that degraded given two channels is very easy to compute. You can compute if a channel is a degradation of another. But in fact, less noisy, just like channel capacity, is quite difficult to compute. So it's rather difficult to tell if two channels have an information theoretic solution or not. But computationally, we can easily tell. And there's a couple extensions. Again, we can extend this to general message spaces, and we can actually get optimal rate, meaning that we can send messages up to the capacity of Bob's channel. And you can do this using standard cryptographic techniques in the computational setting. And finally, we note that our scheme is a universal encoding, meaning that the encoding only depends on Bob's channel and not Eve's channel. So this is nice, because you don't have to really know what the adversary's channel is exactly in order to get this scheme. So thank you.
Any question?
So thanks for the talk. I wanted to ask if you thought that obfuscation was necessary for this to work, or like, why could this not be possible, say, just using public key or something like that?
Yeah, that's a good question. So so for one thing, our setting, so if you didn't want to have the channels, then you actually can't get such a scheme because we're talking about unidirectional communication. So there's no back and forth and there's no shared secrets ahead of time. So in some sense, we do need a noisy channel to allow even secure messaging to happen. But assuming that the other question is, do you need obfuscation? So actually something weaker than this obfuscation could suffice. This is sort of a more standard definition we use, but we really sort of just need like a one-wayness, and that if you send this message across, then you can't completely recover the message, because then you could use an extractor or a hardcode bit on the message. So obfuscation is sufficient thing to create this scheme, but you could probably propose other things that are a little bit weaker and would also satisfy this.
Oh, wait, thank you.
There is also a question on Zoom. Somebody asked, do you require specific probability distribution over the message space to prove security? For example, the message is uniformly distributed.
Okay, yeah, so for our scheme, in the general case, it's just simply a uniform random message that we send across. And actually, really all we require is that the message you send across, it's unpredictable and has the same, like a large number of each input symbol. But we don't require specific distribution dependent on the channel.
Any other question? If not, let's thank the speaker again. The next talk is correlated pseudo-randomness from expand accumulate code. The speaker is Nicolas Ratch.
Possible to do this. Yeah. Cool. All right. Thank you very much for the introduction. Yeah, my name is Nicolas Resch, and this is joint work with Elet Boyle, Geoffroy Couteau, Yves Gilboa, Yuval Ishai again, Lisa Cole, and Peter Scholl. So this talk is concerned with correlated randomness or correlated pseudorandomness. Oh, this forward button. Sorry, was it this green button? Okay.
You may need to move.
Oh, I need to move the. There we go. Yes, I think that was the problem. Great. So this talk is concerned with correlated randomness or even correlated pseudorandomness. And I'd like to start off by pointing out that this is something that you're all very familiar with, even from the very first course that you maybe took on cryptography, maybe the second lecture even. So Alice and Bob are two friends who wish to communicate. So Alice has some message she wants to send to Bob, but the channel might be eavesdropped on. What can these two people do? Well, they could use a one-time pad to securely encrypt Alice's message. So how should we think about this one-time pad? Well, I'd like to encourage you to think of this as some sort of correlated randomness. These are two uniformly random strings, marginally uniformly random, but together they satisfy the equality correlation. Okay, so this is great for secure communication, but we're going to deal with multi-party computation in this talk. So just to briefly remind you all of what this is. Now we have our two friends Alice and Bob, but unfortunately they don't trust each other anymore. But nonetheless, they'd like to work together to compute some function f, which depends on their private inputs x and y. And we want to do this in such a way that nothing additional is revealed about the private inputs. So just for this talk, I'd like you to just think of the case of two parties. Okay, now, even though this is maybe seemingly a more difficult challenge for Alice and Bob to do here, compared to just communication, it turns out that once we have some nice shared correlated randomness, Alice and Bob can run very efficient 2PC protocols. So in particular, once we have these things called oblivious transfer correlations, where essentially Alice has some random choice bit, which picks out one of the two messages from Bob, it turns out that we can have very fast protocols for, say, computing the secure AND of 2 bits. So I don't want you to look too much at the precise details on the slide, but the important fact is that once we have this correlated randomness, we can run very, very fast MPC protocols, essentially by going through the circuit describing the function that Alice and Bob wish to compute and consuming the randomness as required. So this basically describes the MPC with pre-processing framework. Once, at the start, maybe Alice and Bob have to share a lot of correlated randomness, but once this is done, we have a very, very fast, even information theoretically secure MPC protocol. But okay, there is, of course, a drawback here. What's the problem? I mean, the problem is that we typically need very, very long random strings. And this isn't even too surprising. I mean, this first example that I gave you about the one-time pad, we know from Shannon's impossibility results that we need the length of a one-time pad to be at least the length of a message. But of course, cryptographers have developed already since the 80s great solutions to this problem. Instead of sharing a complete one-time pad, you might share, say, a seed for a pseudorandom generator. or even maybe a key for a pseudorandom function, and then you can just generate the pseudorandomness that you need, which is basically like generating, you know, all the correlated one-time pads that Alice and Bob need to communicate. So when it comes to secure computation, I mean, essentially this sort of protocol I was describing on the previous slide would require 2 oblivious transfers per AND gate. And traditionally, unfortunately, we would need a very, very long pre-processing phase with high communication in order to share all this correlated randomness. But fortunately, in the last 6 or 7 years, essentially recreating this idea from secure communication was used in the secure computation framework, where we could imagine sharing short correlated seeds to Alice and Bob, and then they can stretch them, but now generating pseudorandom correlations. Okay, so let's try to make this a bit more precise here. So how would a pseudorandom correlation generator work? Again, we have our friends Alice and Bob, and initially we can generate some seeds. And the point now is that once Alice and Bob have these short seeds, they can run some expand algorithm on these seeds. And now note that this step here requires no communication. So this is just them privately expanding their own seeds. And we just want some certain guarantees. So first of all, you should maybe think of every entry in their expanded seeds. These long strings at the bottom here are just like n independent OTE correlations that they could use when running their favorite MPC protocol. And then we also need that, each of them on their own, if you only see one of them, it looks like a uniformly random string, just like we had for one-time pads. And the security now is also a bit more subtle. I'm not going to go into too many details, but essentially because Alice and Bob don't trust each other, you need it to be sort of the case that even after seeing your own seed, the other party's half only looks, pseudo-random up to this correlation that, we're targeting. Okay, but that's not, that's more some prior work. And so this is the sort of object that we'll be targeting today. But now also just in the same way that we could go from pseudorandom generators to pseudorandom functions when you want, let's say an exponentially long string of, randomness that you can sort of query on demand, we can do something similar. We can ask for something similar with these correlations. And here it's sort of like we would share now some correlated keys to Alice and Bob. And then whenever they need a new they need a new instance of the desired correlation, they can run some eval function. So this could give them, up to exponentially many correlations that they could use in their MPC protocol. And the correctness, pseudorandomness, and security guarantees are just the same. So I won't belabor the point. Okay, so what do we propose in this work? Well, if we think about the pseudorandom correlation generators, they have the effect that all the work is done in the offline phase, essentially. We share these seeds at the start, and then we run this expansion protocol, and then, this expansion step, which is silent. But then when we're actually running the MPC protocol, no more work needs to be done. On the other hand, with pseudorandom correlation functions, all the work is essentially done in the online phase. And this can be a bit of an expensive step. We share these keys at the start, but every time we need a new correlation, we have to run this eval operation. And so in this work, we propose what we call offline-online PCGs, which are sort of a more flexible intermediate point between these two objects. So how would this work now? Let's say we have offline and online keys. And initially, Alice and Bob can share all these keys and then run a silent offline step to generate what I'll call this offline material YA and YB. And now this offline material in and of itself does not actually satisfy the desired target correlation. But one thing that we will guarantee is that it's not too long. It's not, say, if we want 10 million OTs, maybe this is only like 20 million long or something like that. So it's not too much too big. But now when Alice and Bob need a correlation from the desired target correlation, they can run a very, very fast online algorithm. And in particular, we'll be targeting algorithms that have nice locality properties. So they might only read, say, like, I guess our best construction theoretically gets like 40 entries that need to be read from the offline material. Okay, so this is more efficient than what a typical eval operation for a PCF. Okay, and again, analogous correctness, pseudorandomness, and security guarantees. Great, so our main results, our main contribution, I suppose I should say, is a construction of an offline-online PCG from a new class of codes, which we term expand accumulate codes. So if you're wondering why this talk appears in the coding theory session, this is the answer. And what are the sort of the nice features of our construction? The offline phase, it has nice efficiency properties. In particular, it's highly parallelizable and also cache friendly. Hopefully I'll be able to convince you of these properties as I explain the codes. And furthermore, the online phase has this low output locality that I promised. Great, so without any further ado, allow me to get into a brief discussion of how we could hope to construct these pseudorandom correlation generators or functions, or eventually this offline-online variant. So in order to describe how this works, it's best if we talk about what's called the vector oblivious linear evaluation, or Volley correlation, which you can just think of as an additive secret sharing of a scalar vector product. If you really want these OTs, once you have a long Boolean correlation, you can get a whole bunch of OTs with one additional hashing step. So basically, this is a very good thing to target. And just pictorially, I'd like you to encourage of, we want to simulate this box, which just outputs a vector A and C naught to Alice, and a vector B and C1 to Bob. Sorry, a scalar B and a vector C1 to Bob, and B times A is equal to C naught plus C1. So how could we go about doing this? Well, let's consider a certain function. This is basically, I'm just taking the vector B times A, and I'm rewriting it as a function from the integers 1 to n to the field f. So nothing fancy is going on here. But we sort of want to additively share this object. So we could talk about trying to additively share this function between Alice and Bob. And this brings us to the topic of additive function secret sharing, which is a topic that's been studied intensively in recent years. So we want to come up with a way to design some keys that we can give to Alice and Bob, Ka and Kb, such that they can both privately, without any communication, run some eval operations. And then it's guaranteed that whenever they run this eval operation on a given input x, they get an additive secret sharing of the function f applied, evaluated at the point x. Okay, and now sort of a naive or simple solution to this problem would be just to say, okay, look at my function and share it, share this truth table. But we're going to look for something much more efficient. Ideally, the key should be sort of logarithmic in the size of this truth table. So doing this for general functions is maybe not doable, but we can do it for special classes of functions. So in particular, sort of the first functions which were studied were these point functions, which are just functions that take at most one non-zero value, let's say. And once you can sort of do a function that takes at most one non-zero value, we could also say do functions that take at most t non-zero values just by blowing up the keys by a factor of t, say, because we just need t sharings of point functions. So we can basically share functions that take, say, at most t non-zero values where we think of t as not being too large. Okay, so what does this mean returning to the function that we wanted to share? If so long as this vector A was sparse, that means this function f of x, which is b times a sub x, that will be a function that takes at most, say, t non-zero values when a is the Hamming weight of t. Sorry, t is the Hamming weight of a. Good. So this is already allows us to say essentially that we have a way to do a sparse Borlée correlation. So I'll introduce some new names here, which hopefully will be clear in a second. But basically, we can share random vectors that satisfy the correlation b times e equals c naught prime plus c1 prime with the additional caveat that this vector e is sparse. So how could we hope to convert this into a genuine vector OLE instance? Well, if we have some matrix H, which is some linear compressing map, let's say, and we apply it to all these vectors, then we'll get some new vectors A, C naught, and C1. And firstly, just because of the linearity of H, we still preserve the desired Borlée correlation. So nothing there has gone wrong. Now the question is, should we expect that these vectors all kind of look pseudo-random up to this correlation? So in particular, the non-trivial part here is that this vector A up here is the image of a sparse vector. So why should we expect it to be to look uniform? Fortunately for us, there's sort of a well-studied assumption. I'm calling it LPN here, learning pairs with noise. Maybe to use some more expressive language from the previous talks, we should say, I guess, the decisional variant of the syndrome decoding problem. If you choose H uniformly at random, this will indeed work, that this vector A will look computationally indistinguishable from a uniformly random vector. But we can be a bit greedy here. So if you recall also from, I guess, the first talk, we talked about Alexanovich's construction and how a uniformly random matrix is a bit too much to store. Could we hope to also get some better efficiency properties here if we choose the matrix H more carefully? And indeed, a certain line of works has been working on exactly this question. Great, so this brings us to our choice of the matrix H, which leads us to these expand accumulate codes. So how should we choose H? What we need is that when we multiply it by a sparse vector, a random sparse vector, it should be computationally indistinguishable from uniform. You could think of this as some sort of pseudo-random generator type behavior, because the vector E, if it's low weight, is sort of a low entropy seed that we want to make look uniform. So if we want this to be as efficiently computable as possible, a very nice solution maybe would be just to take H very, very sparse. Say maybe it only has like 10 non-zeros per row, and then you just need to do, look up like 10 coordinates in E and sum them up. But unfortunately, it might not take you too long to convince yourself that then the problem then was that the output of H times E will then also be sparse. Right, so if I take a dot product between a sparse thing and another sparse thing, the output is going to be biased towards 0. So in particular, I can distinguish it from uniform. Okay, but in some sense, what we do is maybe sort of the simplest trick to sort of make this work. Okay, and what do I mean in this sense? Let's again start with a sparse matrix, and we're going to sample it randomly. So for concreteness, think of just making each entry 1 with some probability p, and we'll choose p to be quite small. So this alone will not work. But I'm going to multiply it by some matrix that I'll call the accumulator matrix. Okay, and this is just a matrix with 1s on and above the main diagonal. And then just the product of these two matrices will give us this matrix H that we wanted. And so in some sense, we think of this sparse matrix as an expansion step, and then this next matrix A is the accumulator matrix. So hence the name expand accumulate codes. And now how should we think about this accumulation step? Well, if I put down a sparse row in this sparse matrix here, what happens on the generator matrix? Basically, the corresponding row will be sort of a union of intervals where like the endpoints are determined by the 1s in the sparse matrix. Because essentially this accumulator matrix, what it's really doing when you do like a row multiplied by this accumulator matrix, it's just computing the prefix sum. Right, so it's just saying the first coordinate is the sum of, the first coordinate is itself, the second coordinate is the sum of the first 2 things, the third coordinate is the sum of the first 3 things. All this I'm doing modulo 2 just for concreteness. Okay, so this is exactly how we can go and construct our offline online PCG from using these codes. So just to put everything together. So offline, we're going to do this accumulation step. So this is, how we go from the seed, which is, being represented by this sparse vector here. We do this accumulation step. So we just compute the prefix sum of this. I guess here might be the suffix sum since I'm doing it from the column now. But in any case, we do a very fast parallelizable and cache-friendly step. So this is all done before the protocol begins. And then when we do this online step, every time we need a new correlation, we basically just take one of the rows from this sparse matrix and compute the dot product with this offline material, these YAs or YBs that we pre-computed. Great, so this already explains our main construction, but it leaves out an important detail. Why should we believe that this is computationally indistinguishable from uniform? Why should it be that all these bits that we get once we do this sparse vector multiplied by the accumulated error vector, that it should look uniform? Okay. So in order to answer this question, the ideal thing, we would like to be able to say, reduce to some well-known problem. I mean, the natural candidate here would be something like learning parity with noise. Alternatively, what we do is, okay, we can't necessarily reduce to this known hard problem, but we can rule out sort of a broad class of attacks. So I hope I don't say anything that offends anyone too much in this audience, but I believe that sort of almost all of the attacks that would be relevant to the sort of setup that we have boil down to this following strategy, where basically you look for some vector, some row vector now, and left multiply it by your matrix H. So recall the matrix H is public, so your adversary can look at this and find this, what I'll call an attack vector X. And then basically when it's given a sample Y, which is either uniformly random or of the form H times E, it'll just compute this dot product. And the point now is that if X transpose H were sparse, then in the case where Y is of the form H times E, then that inner product will again be biased towards 0 because you'll end up with a sparse vector inner product with a sparse vector. So that will be biased towards 0. But if it's uniformly random, this will be an unbiased bit. And so this has been termed the linear test framework. Okay, so these are the sorts of attacks that we're going to rule out. And so how can we actually do this? Well, it turns out, if you think carefully about what the test does, all we really need to say is that there are no low weight non-zero vectors in what I'll call a code now, the set of all elements of the form X transpose H. So from a coding theoretic perspective, this is now just a code, and we want to show that it has good minimum distance. So this is sort of a classic problem from a coding theory perspective, although for a new class of codes. And essentially that's exactly what we do. We rule out linear attacks by, say, just to give a sample of the parameters, once the density is roughly log n over n, we'll get linear minimum distance with inverse polynomial failure probability. If you're really unhappy with the inverse polynomial failure probability, you could say take log squared n over n. But to be perfectly frank, we're mostly interested in getting very good concrete performance. So the precise asymptotic parameters you can play with as you like. Good. So unfortunately, I don't think I really have time to dive into the details of how we prove this. If you do have any questions on this topic, I'd be more than happy to answer them later offline, or of course, the details are all in the paper. But now, just with my remaining time, I'd like to say a bit more about the concrete efficiency, since that is really sort of the goal here, is to get concretely efficient PCGs. So in the offline phase, these are all some estimates, but it should take about 100 milliseconds to generate the offline material for about 10 million OTs. And since these prefix sum operations are very easily done in parallel, we can get sort of a factor K speed up as soon as K processors are available. Okay, and now in the online phase, so theoretically, it seems like, for reasonable parameters, for 128 bits of security, it should take about 40 lookups. So that's basically the density of all the rows that we need to do the inner product with, plus this additional hash operation to get the OTs. Now, if we want to be very aggressive, based on some experimental evidence, we think that it might even be feasible to have a much smaller number of lookups, even 7. So the intuition here is that, okay, so for this linear test framework, basically, the adversary is supposed to look at the matrix H, then come up with this attack vector for which X transpose H is sparse. In principle, though, if we just want computational security, I mean, we could say that maybe it's hard to find such an attack vector. And basically, we don't know how to find an attack vector once, the density is, say, like 7. Okay, but this is, of course, very conjectural at this point, and I think this definitely merits further cryptanalysis. Okay, so just to sort of recap what we did here, we talked about expand accumulate codes, which had a highly parallelizable offline phase, which is also cache friendly, and also the online phase had low output locality. And now just to compare to some sort of competing approaches here, there was a recent proposal called Silver, which basically lacks the parallelizability of our proposal. Also, this one didn't really come with theoretical analysis. It came with very rigorous sort of experimental analysis, but still doesn't have the theoretical analysis that our proposal has. There are also these codes which are called repeat accumulate codes. So they have 2 accumulation steps, which sort of kills the cache friendliness. So they don't have the nice properties that we have. Although I should say that our construction of expand accumulate codes was very much inspired by these sorts of codes. So yeah, so that's sort of the status of things. And I guess I don't have too much time left, and I don't want to keep you too late, especially since this is the last session. But I'll try to hint at some further results, because this is not everything that we do. So first of all, we do also construct pseudo-random correlation functions. That was another one of our contributions. The real challenge here is that basically, recall we need to sort of create an exponentially long vector of correlations that we can access. So in particular, say if this error vector is exponentially long, we're not going to be able to compute this accumulation step. Even storing it is far too expensive. But what can we do instead? Well, we can look at actually what A times E looks like, and try to directly function secret share it. Instead of function secret sharing the vector E, we can function secret share the accumulated vector A times E. And now it turns out, once again, this is some sort of, I think it's now suffix sum, assuming I didn't make a mistake here. It's some sort of vector which looks like this, which we could think of some sort of, interval function or a small sum of what I'll call comparison functions, which are just functions that, take a non-zero value below a certain cutoff Y, and then are 0 above the cutoff Y, or even, the inverse of that. And fortunately for us, there exists, efficient FSS schemes for these sorts of comparison functions. We can actually even use a relaxed variant, because one of the parties, I guess, Alice, gets to know the value Y, so this allows some savings. But essentially, we can do some sort of function secret sharing to get a full PCF construction. And we can even get PCFs for some other sort of correlations, like general degree 2 correlations. There we need to share kind of 2-dimensional interval functions, so like a product of these 2 comparison functions. But in any case, all these details are available in the paper. Now, we have one more contribution, which is very disjoint and orthogonal to everything I've said thus far. So I'll try to briefly hint at it, but this might be a bit of a change in tone. So in this offline, the offline step, basically, we do this function secret sharing for this, vector B times E. And then we need to expand them out into the 2 additive sharing, C0 and C1, which corresponds to doing some sort of eval all operation. We need to evaluate all of the different secret sharings of your function. And it turns out that all these FSS schemes are built from punctured PRF. And in order to do this eval all step, hand waving a lot here, basically the bulk of the work is to compute an entire GDM tree. So these sort of structure where you have the key at the top, and then you go down the tree, and the left child is H0 of the parent, and the right child is H1 of the parent. Okay, so in order to sort of save on hash calls, we propose the following sort of modification, where instead of doing independent hash calls on both the children, you could call the hash for the left child, and then for the right child, you call the hash again on the parent, and then you XOR it with the value of the parent. So this will unfortunately not yield a genuine punctured PRF. It's not too difficult to see that sort of a certain value which is supposed to be indistinguishable from uniform is distinguishable from uniform, but it's still unpredictable in a certain sense. So this already gives us something which can be used to say construct PCGs for OTs. But if you want a genuine punctured PRF, you just need one additional hashing layer. So we talked sort of a lot about the different sort of trade-offs that you could hope to do in this offline stage in the paper, including potentially changing the arity of the GGM tree if you want some other savings. But this is all. And also, I should say, this is a proposal that sort of works in the random oracle model. If the ideal cipher model, we have a proposal with that lacks theoretical analysis. Although for the random oracle model, we do have theoretical analysis. Okay, I believe I'm over time, so allow me to quickly recap. So we talked about generating correlations. In particular, we talked about this sort of Boolean blocks that we hope to instantiate. And the way we proposed to do this was via these offline-online PCGs. This is the picture to keep in mind. The special class of codes that allowed us to get our construction with these expand accumulate codes, and we gave some sort of theoretical analysis to show that they do, in some sense, they basically provide a PRG, at least according to, against the class of attacks. And then we had a few other results that I briefly sketched at the end. All right, thank you very much. And oh, I guess that's the end. Thank you.
Any question? Okay, maybe I can ask a question here. So you mentioned that in the offline phase, it is cache friendly, and the online phase, you need to do a random access. Does that mean that the output of the offline phase is actually something linear to the number of VOLE that you need to generate?
Sorry, linear in what?
Linear in the number of VOLE that you need to generate.
The online phase?
The offline phase, the
Offline
output
phase,
of the
yeah,
offline
yeah,
phase.
It will be, yeah. So for the PCG construction, yeah. But basically, you can parallelize a lot of the work because essentially you need to accumulate the vector that you accumulate will be sort of linear. The length of it will be linear in the number of OTs you want to generate. I think like maybe like 5 times longer, I think is a certain proposal we have. And then yes, from there. So once you, yeah, so that step will be linear in the number of OTs. Yeah.
I see. So the seed generation is probably like a first part of the offline phase.
Yeah, yeah.
I see.
Oh yeah. So essentially something I was kind of skipping was basically, we compressed everything down to short seeds, basically to share the keys for the FSS and maybe a tiny bit of other material. But this, you can just use some sort of inefficient Npc protocol to share because it's so small that, even if it's inefficient in the size that the amount of material you need to share, it's so small that it's immaterial. Yeah. Or asymptotically negligible. Yeah.
Any other question? Except my question. Okay, let's thank the speaker again. Yeah, so there will be no talk in this room. Everything else this afternoon is on the other side, except the rump session, which is very